Welcome to Paper Trail, where we make academic research accessible and engaging. Let's see what the evidence says. For years, AI models have tackled text and even images with impressive sophistication, but audio has often been considered the neglected stepchild of multimodal AI. Now, a new model from NVIDIA and the University of Maryland, called Flamingo Next, or AF Next, claims to be closing that audio gap.
And it's not just claiming it. The data shows this open-weight model is actually outperforming proprietary systems like Google's Gemini 2.5 Pro on some critical long audio reasoning tasks. This represents a significant leap in how AI can understand and process extended sound.
That's a bold claim. It's often taken for granted how easily a 30-page PDF can be parsed. But why has asking a neural network to make sense of a chaotic 30-minute audio file been so much harder than handling a text document of similar length?
It really comes down to the fundamental nature of the data. Text is inherently discrete. A word is a distinct, isolated unit of meaning. It has clear boundaries. You can highlight it, copy it, refer back to a specific page or paragraph. Audio, on the other hand, is continuous, it's overlapping, and crucially, it's temporally fleeting. A 30-minute audio file isn't just a sequence of words, it's a dynamic physical waveform. It contains multiple, parallel streams of information: a person speaking, a siren passing, room reverberation, perhaps background music, or even an air conditioner humming.
So a model can't just transcribe the speech like a traditional automatic speech recognition system. It has to disentangle all these concurrent sounds.
Exactly. And then it has to identify each of them and maintain their temporal relationship over potentially very long stretches of time. Think about trying to follow a complex conversation in a busy coffee shop, noting who said what, when a song started playing, and when the espresso machine whirred, all while maintaining the narrative thread. That's an incredibly heavy computational lift for a neural network. Historically, the AI community solved this by building narrow, domain-specific tools. One model for speech-to-text, a different one for music tagging, another for environmental sound classification. AF Next abandons that fragmented approach, aiming for a single, unified generalist model.
So it's designed to evaluate a symphony, transcribe a multilingual conversation, and identify a specific bird species, all within the same neural architecture? That's ambitious. How did they even begin to build something like that? What's the underlying structure that allows for this generalist capability, and more importantly, that 30-minute context window?
The architecture is described as a 4-component pipeline. It starts with an enhanced audio Flamingo whisper encoder, or AF Whisper. This component doesn't just feed raw audio waves into the system. Instead, it uses what are called 128-bin log-mel features.
For listeners, how should a log-mel spectrogram be understood?
Think of it as a visual representation of sound. It maps the spectrum of frequencies in an audio signal over time, but crucially, it does so on a scale, the Mel scale, that mimics how the human ear actually perceives sound. So it's processing audio in a way that's more aligned with human hearing.
That makes sense. But even with that sophisticated encoding, a 30-minute audio file is still massive. How does the model manage to swallow all that information without being overwhelmed?
This is where a crucial engineering choice comes in, a 30-second chunking strategy. Instead of trying to process the entire 30-minute audio file at once, which would indeed overwhelm the model's memory, AF Next processes the audio in 30-second, non-overlapping chunks. Imagine you're reading a massive, epic novel. You don't try to hold every single letter of the entire book in your head simultaneously. Instead, you read it chapter by chapter, processing the information, summarizing the key plot points, and remembering where you are in the overall narrative. That's essentially what this chunking strategy allows the model to do with audio.
So it's breaking down the problem into manageable pieces. What happens to these 30-second chunks after they're processed by the AF Whisper encoder?
The output from these audio chunks then passes through a 2-layer multi-layer perceptron, or MLP, adapter. You can think of this as a translator. It takes those acoustic features and translates them into a format that a text-based large language model can understand. This is key because the brain of the operation, the component that actually performs the reasoning, is a large language model from the Qwen 2.5 family extended to handle a massive context window. By chunking the audio and efficiently translating it, the researchers expanded the model's context window to 128,000 tokens, enabling it to natively ingest and hold up to 30 minutes of complex audio in its working memory.
That's a huge context window. But a model is only as good as its training data. Many impressive models have fallen short because their data wasn't robust enough. How was that addressed for AF Next?
They recognized that prior audio models often suffered from being overtrained on relatively sterile, short-clip academic datasets. To break that bottleneck, they scaled the training data to an unprecedented level, over 1 million hours of audio, comprising approximately 108 million individual samples. This wasn't just expanding existing datasets. It involved incorporating over 200,000 long-form internet videos ranging from 5 to 30 minutes, alongside millions of real-world short audio skill samples and multi-audio instruction examples. It's moving beyond curated academic benchmarks into the messy, complex reality of internet-scale data.
1 million hours of audio data is indeed massive. But the real intellectual centerpiece of this paper, the part that seems to truly unlock the model's reasoning capability over these long audio stretches, is something called temporal audio chain of thought. Chain of thought prompting for text and even vision models has been discussed. Why did those approaches fail when applied to audio?
The problem with applying standard chain of thought to audio is that in a text document, the evidence is static. You can always point to a specific sentence on page 4 and refer back to it. In audio, as discussed, evidence is temporally dispersed and fleeting. Previous audio-caught datasets were limited to short 10-second clips. If a model tried to reason over a 30-minute file without a proper temporal grounding, it would hallucinate, or its internal logic wouldn't be tethered to anything concrete in the audio stream. It would lose track of when things happened, which is critical for understanding cause and effect.
So how does temporal audio chain of thought, or TACOT, solve this? What's the breakthrough?
The methodology explicitly forces the model to anchor each intermediate reasoning step to a specific timestamp before it's allowed to produce a final answer. It can't just say, this happened and then this happened. It has to say, at 2 minutes and 15 seconds, X occurred, which then led to Y at 5 minutes and 30 seconds.
That sounds incredibly challenging to train. How was a model taught to behave that way?
They had to build an entirely new dataset for it, called AF Think Time. This dataset consists of roughly 43,000 question-answer thinking triplets, drawing from highly complex audio sources like movie trailers, audio recaps, long-form multi-party conversations, and, notably, mystery stories.
Mystery stories. That's a notable choice.
It's the ultimate test of temporal reasoning. To solve a mystery, a clue heard at, say, minute 2:15 must be connected to a revelation at minute 28:40. The average thinking chain in this dataset contains over 446 words, forcing the model to produce deep, extended reasoning that's grounded in a verifiable timeline.
And how is this timestamp anchoring mathematically possible? How does the model actually know what time it is in the audio?
This is where rotary time embeddings, or ROTE, come into play. Traditional language models use discrete positional embeddings. They might say, this is token 1, this is token 500. But for audio tokens, which are produced at a fixed 40-millisecond stride, ROTE interpolates these discrete positions and grounds the positional representations in actual timestamps.
So instead of just a sequence number, it's literally mapping to this happened at 14 minutes and 22 seconds?
Precisely. This is critical because it allows the model to calculate the exact temporal distance between two events, regardless of how many tokens separate them. It transforms the model's internal logic from an uninterpretable black box into a verifiable timeline of evidence. It's not just recognizing a dog barking and a glass breaking. It's recognizing that the dog barked at 4 minutes and 12 seconds and the glass broke at 4 minutes and 15 seconds, allowing it to establish a causal or sequential chain of events. That's a significant methodological leap.
The engineering and design described here is truly clever. So how does this all translate into empirical results? What do the benchmarks show for AF Next, especially against those proprietary models mentioned earlier?
The paper tests AF Next across more than 20 audio understanding and reasoning benchmarks. The most critical for this discussion is Long Audio Bench, which specifically tests a model's ability to retain and reason over long context windows. Here, AF Next Instruct scored 73.9.
And how does that compare to its predecessor or competitors?
Its predecessor, Audio Flamingo 3, scored 68.6. But most strikingly, Google's proprietary Gemini 2.5 Pro scored 60.4. Beating Gemini 2.5 Pro by 13.5 points on long audio reasoning is a staggering achievement for an open-weight model. It really validates the temporal audio chain of thought methodology. It also edged out Gemini on the MMAU Pro benchmark, 58.7 to 57.4.
So it's demonstrably better at long-form audio reasoning. But does it sacrifice basic utility for these advanced reasoning capabilities? How does it perform on something like simple speech transcription?
On traditional speech metrics, AF Next holds its own. For instance, on the LibriSpeech Test Clean Word Error Rate, or WER, AF Next achieved 1.54, which the paper notes is the lowest among comparable large audio language models. So it hasn't traded foundational accuracy for advanced reasoning.
And since it's a generalist model, what about music? That's notoriously difficult for AI due to dense, layered instrumentation.
It shows significant improvement there too. On the Medley Solos DB benchmark for instrument recognition, AF Next jumped to an accuracy of 92.13. That's a massive improvement from its predecessor, Audio Flamingo 2, which scored 85.80. It also outperformed prior open-weight models like Qwen Audio on the NS Synth benchmark for source and instrument classification. These numbers underscore the strength of its unified, generalist architecture.
The numbers are impressive, showing a strong trajectory for open-source AI. But a score of 73.9 on Long Audio Bench, while beating a major competitor, still means the model fails roughly 26% of the time. What else needs to be known about the practical implications and any remaining limitations?
The researchers didn't just release a single model. They open-sourced 3 distinct variants on Hugging Face, each tuned for specific use cases. There's AF Next Instruct, which is the daily driver for general question answering, ASR, and multi-turn chat. Then there's AF Next Think, which is specifically optimized for explicit multi-step reasoning, producing longer, time-stamped grounded reasoning traces. And finally, AF Next Captioner, designed for dense, long-form captions and detailed scene breakdowns, like for a nature recording.
This strategy for deployment is notable, but the fine print with these open-source releases always needs to be read. Is there a catch here?
There is, and it's a significant one for commercial adoption. The paper explicitly states, due to the licensing and scope of the training data used in the work, all releases will be under a research-only license.
So while the model weights are open, a startup or company can't just download AF Next and build a commercial product around it. Why is that?
It goes back to the massive scale of the training data. To achieve that 1 million hour volume, researchers inevitably rely on internet-scale data, which includes things like YouTube videos and podcasts. The copyright ambiguity surrounding this data necessitates a non-commercial, research-only release to mitigate potential legal risks. It's a recurring challenge for models trained on such vast, diverse, and often uncurated internet content.
And what about real-time interaction? Voice modes for models like ChatGPT have been seen. Can AF Next do something similar?
Not in its current open-source release. The Hugging Face repository explicitly notes a major limitation regarding real-time interaction. While the broader AF Next project discusses streaming text-to-speech and voice-to-voice interaction, those specific components are not part of this open-source checkpoint. So AF Next, in its current form, is an incredible analytical tool. Audio in, text out. It can process and reason about complex audio, but it's not a real-time conversational agent like a voice assistant that can interrupt you or hold a fluid, low-latency spoken conversation. It's an analytical engine, not an interactive one.
So to summarize, this paper and the AF Next model represent several crucial developments in AI's ability to understand audio. First, it shows the end of the siloed approach, demonstrating that a single unified architecture can master speech transcription, environmental sound analysis, and complex music understanding simultaneously.
Absolutely. And second, the core innovation lies in making time the anchor. Temporal audio chain of thought, enabled by rotary time embeddings, forces the AI to attach timestamps to its logic, making its reasoning interpretable, verifiable, and highly accurate over those critical 30-minute stretches.
Third, the benchmark data, especially that 73.9 on long audio bench, provides compelling evidence that open weight models, fueled by academic and industry partnerships, can now truly challenge and even outmaneuver proprietary systems from major tech companies in specific, complex domains.
And finally, this leap in performance wasn't just algorithmic. It required curating over 1 million hours of data. This demonstrates that the AI industry is aggressively moving beyond sterile academic datasets into the messy, internet-scale reality to train these next-generation models.
This all suggests a significant step forward for understanding complex, real-world audio. But given the research-only license and the challenges of deploying these internet-trained models commercially, what do you think is the biggest hurdle for this kind of technology moving from the lab into widespread application?
That licensing issue is certainly a critical one. How can vast internet-scale data be responsibly leveraged for training without infringing on intellectual property or stifling commercial innovation? And beyond that, how can the analytical tool stage be pushed past to truly enable real-time, nuanced interaction with these increasingly capable audio models?
That wraps up this episode of Paper Trail. Join us next time as we dig into more research worth talking about. If you liked what you heard, share it with a friend.
Keep reading the fine print.